All right, lecture 20. So we were talking right before class, so this is the end of week 7, and then week 8 is kind of not a full week, so we're kind of halfway there, you know. It doesn't, I don't know, it doesn't feel like that. I don't know how to put it. It seems like the semester's gone by fast and slow at the same time. I don't know. I don't know if that makes any sense, but we think we were saying earlier, like the first part of the semester seemed to drag on, and then, you know, so maybe that's just me. Okay, how did, hopefully homework 3.7 was a little more straightforward than maybe 3.6. And what I'll say is this homework's pretty gentle in terms of it's a lot shorter. It's really short. In fact, the next 2 assignments are going to be pretty short. I would say that you could probably knock this one out in a matter of minutes. So it's a pretty gentle assignment. Don't forget, we do still have our exam on the 18th, so in 2 weeks, but it's after the break, so we don't have any exam next week. So we'll do our review, and then we'll have the exam on Friday. Today, we're going to start rigid body equilibriums. This is a new module in the class, and this is the most statics of all statics topics in the whole class, because this is really where the principles of static equilibrium are going to be applied in order to assess equilibrium of more, I'll call it, real systems. And what I'll say is we've done static equilibrium problems before, but we were restricted to systems where all the forces all met at a common point. Now we're not. Now we can handle equilibrium of pretty much any system that is subjected to forces. So the forces can be non-concurrent. Now I'll say a little bit about terminology. We use the term rigid body equilibrium because at this point in your engineering education, we do not assume that the bodies can deform. If I take a 200-pound force and place it on this table, the table will deform. It will flex. It will bend. Okay. You'll take either Engineering 216, or I think it's Biomedical 302, where you discuss mechanics of deformable bodies, okay? Where what you'll do is you'll take results from a static equilibrium analysis and then say, what are the stresses, what are the strains, what are the deformations? Because if you understand stresses and strains and deformations, you can then start selecting materials for applications. You can start saying, here's how deep the beam needs to be, here's the required material for that biomedical implant or whatever. So again, you know, you're taking it in stages, and this is sort of stage 1, is being able to perform these rigid body analyses. You then consider the deformation later. Okay, everybody got the code? All right. Okay. So yeah, so it's a really, really kind of exciting day in terms of what we do here in Engineering 213. So last time, and really for the past couple of lectures, we've arrived at this idea of an equivalent system, okay? And the idea of an equivalent system is that the forces in system, if the forces and moments in system 1 are the same as the forces and moments in system 2, then those systems are equivalent. And now what we're going to do is extend that concept into equilibrium by saying that for a system to be in equilibrium, the sum of all force vectors must be 0, and the sum of all moment vectors must be 0. Now I put here on the board just a way of describing, and I don't think I've really used this specific notation before, but this could be a way of describing a resultant vector and a resultant moment vector, right? Which, so if I'm looking at forces, right, the resultant vector is really the sum of all the force components in the x direction times I, the sum of all the force components in the y direction times j, and the sum of all the z components times k. In other words, like I'm just adding up all those coefficients, right? Add up all the coefficients in front of I, in front of j, in front of k, respectively. And I think what's new is this notation. I don't think I've written it this way, where for moments, it's the same idea. Add up all the moment coefficients in front of I, the moment coefficients in front of j, the moment coefficients in front of k. Make sense? Okay. So this would be a resultant force vector and a resultant moment vector. And what I've got here are really 6 independent terms in 3D, right? 3 force expressions, 3 moment expressions. So if I was looking at equilibrium in 3D, I would say in 3D that this needs to be 0, this needs to be 0, 0, 0, 0, 0. So I have a total of 6 equations that I would have to solve. So up until now, remember how we were doing 2x2 systems of equations and 3x3 systems of equations? Like if we were really doing a full bore 3D problem, we would have 6 equations, 6 unknowns. And so that would be, let's just put it like this, we're not doing that on an exam. that would be incredibly labor intensive. A lot of the 3-dimensional problems that we're going to do, and we'll tackle a lot of this over some of next week and the following week, but a lot of the 3D problems that we're going to do are sort of restricted in a way such that you can do them by hand. I don't expect anybody to solve a 6x6 matrix by hand. That would be very punitive, okay? Software programs can do it, and they can just, chug out stuff no problem, but not for the purposes of educating. Again, we're going to take it slow and then ratchet it up a little bit to make sure that we understand the fundamentals. Now, this is what a system would look like in 3D. What about a system of vectors in 2D? Well, if we were talking about forces in 2D, we would not consider that, right? We wouldn't consider that because we wouldn't have any forces in the 3rd dimension. What about the moments? Which moment term is the only one that exists in 3D? If you have forces across the x-axis and the y-axis, then your moments spin about the z-axis, right? So these terms go away in 2D, right? So 2-dimensional problems are not 6x6. 2-dimensional problems are 3x3, okay? In other words, in 2 dimensions, all we have are the sum of the forces in the x direction, the sum of forces in the y direction, and the sum of moments. That's all we have to deal with in 3D. And what's going to become evident today is that, if you were to treat problems arbitrarily, every single static equilibrium problem would be a 3x3 system of equations. But we can be crafty and choosy in regards to how we solve a problem to make the math very, very easy. And that's going to be kind of a theme of some of the problems that we do over the next few lectures, okay? So in other words, if we're choosy about selecting locations about which to sum moments and so on and so forth, will make our life easier. For example, do you remember the last problem that we did in class? The foundation problem, the square math foundation problem. We had the columns. Do you remember how we said we're going to take moments about the origin? Do you remember that? Remember how one of the forces went through the origin? How much moment did it generate? 0. Because we selected our point of interest as the origin, and one of those forces went through the origin. If you have a point and you have forces going through the point, there is no moment, right? So you can be choosy about how you write your equation and what order in which you choose to solve these equations, and you can make your life a lot easier. And that'll become a theme of the example that we do later. Okay. Everybody good so far? All right. Now, what we're going to be doing, just so everybody's aware, what we're going to be doing is solving for support reactions. And support reactions are pretty much the theme of a rigid body equilibrium analysis. So what I mean by that is, here's a table, here's me sitting on the table. What are the forces required to keep everything, to keep the system in equilibrium? Okay, so just to throw some common sense into this. If I'm sitting right square in the middle of this table, there's 2 legs, a leg here and a leg here. Okay, if I'm in the middle, right, half of my load has to be, half of my weight has to be resisted by this leg, half of my weight has to be resisted by this leg. Independent of all these fancy, cross products and forces and all that, these have to comport also with just basic common sense, right? Which they do, okay? But basic common sense says that, half of my weight would go to either one. Now, would it also make sense, instead of me being in the middle, right? What if I were to scooch over here a little bit? This leg is going to have to hold up more than this leg, right? Make sense? So what we are trying to figure out is, what are those forces that are necessary to keep me in equilibrium? And so when we say support reactions, I apply an action to a system, the system responds with a reaction, right? That's why we call them reaction forces. Now, the number of reaction forces and how we assign those reaction forces is a function of what boundary conditions exist for the problem. Okay, with me so far? Okay, so I have here an image on the slide. Anybody recognize that? Where is that? It's right out here, isn't it? Right. This is right out here between the two engineering buildings. And so what I'm pointing out are these columns. Okay, these columns that are supporting the load from the canopy and transmitting that load to the ground. Okay. Now I'm being a little bit of a structural engineer here in this example, but I think it's a very visceral example that I think you can wrap your head around. Okay. So here's column A and column B, and for the purposes of our discussion, let's assume they're basically the same column. I'm focusing here on the top and here on the bottom. Okay. Now the bottom is probably encased in concrete. And not only is it encased in concrete, but it's probably embedded some depth into the ground. With me so far? So it's going to be like, does anybody have a ruler, like a flexible ruler? They have one? I'm just curious. You have one?
I think I do.
You do? Okay. Oh, this is perfect, perfect. Okay. So imagine here that this is the column, okay, and it's embedded into the ground, okay? So imagine my fist is the concrete that is supporting the column, right? So if I apply some load to the column or some force like this or anything like that, okay, not only is my fist able to prevent translation, you know, if like here's the column and I apply a load, not only is my fist preventing the column from moving this way, it is also preventing this point right here from rotating, right? Think about this like if it was a calculus problem and I were to do this, right? What would the slope of the tangent line be right here? It'd be vertical, right? So we are preventing translation and rotation at this point, right? So this would be what we would call maybe a fixed boundary condition. And that fixed boundary condition would withstand both forces and moments. Okay, with me so far? Now, this boundary condition here might behave much more like a pin. In other words, the pin, like, so imagine I'm, instead of like a fist, maybe I'm just sort of holding it with my finger. In other words, you know, it won't translate, but maybe it'll rotate. Like my finger can maybe hold it in place, but it can't prevent it from sort of doing that. Does that make sense? Like if I were to keep my finger here and I were to move the bottom, it's not translating, but it's certainly rotating, right? So maybe a pin boundary condition would have unknown forces, but it wouldn't have unknown moments. Does that make sense? So to give you kind of an idea, here, let me give you this back before I steal it from you. Here you go. To give you kind of an example of how a pin boundary condition would behave, like let's just take the hinge here in this door, okay? So this door has a hinge boundary condition right here, right? So if I apply a moment to this hinge, it freely deforms, right? It freely translates. But I can't take this and yank it like this or push it like this. Like it's preventing that motion, right? It's preventing translation this way and this way, but it'll freely rotate. So for example, for a pin boundary condition, we're going to see the symbology here in a second, but for a pin boundary condition, we'll have an unknown force in the x direction, an unknown force in the y direction, but we won't have an unknown moment because it can't resist it. Does that make sense? So the boundary conditions that we assign are a function of what's going on in the real world with the problem. Sound good? All right. Now I am using some structural engineering examples here just to sort of make the point, but whether we're dealing with a mechanical engineering system or even a biomedical engineering system, there are certain classes of boundary conditions that you'll see in pretty much any type of system analysis problem. Doesn't really matter the field, the idea is going to kind of be the same. Now, if you open up your textbook is going to have oodles and oodles of different types of two-dimensional support conditions, okay? For most standard analysis problems that you will find in engineering context, whether it's civil engineering or not, doesn't really matter. For most typical problems, you will have three main types of boundary conditions. The first is called a pin boundary condition, okay? So when I draw that out maybe on the board or here on the screen, I'll typically use a triangle, okay? And I kind of use a triangle because, they usually actually kind of look like one. And a pinned boundary condition will resist motion but not resist rotate. Like it'll resist translation but not rotation, okay? So in terms of its unknowns, it will have a potential unknown in the x direction and a potential unknown in the y direction. Now I am being very clear here when I use the word potential because it is very possible that, for example, this unknown is 0, okay? I'm just saying it's there, okay? Its magnitude might be 0, but it's there. Does that make sense? Okay, so this is a hinge boundary condition or a pinned boundary condition. The other common one is a roller, okay? So a roller is intended to only withstand forces in one direction. So it will allow rotation and allow translation in one direction. And to be clear, these boundary conditions are mathematical abstractions, okay? They are meant to represent real-world contexts as much as possible, but it is typically up to you as the analyst to apply the appropriate boundary condition to your problem. And these types of things are the discussion of more advanced mechanical engineering courses, more advanced biomedical engineering courses. Depending upon your problem, the boundary condition that you apply is going to make sense to what you're talking about, okay? Does that make sense? Let me give you an example. And I'm sorry, I'm a bridge engineer, so for you biomedicals, I'm going to talk to the bridges a little bit, but you'll see the point. Okay, so when you're constructing a bridge, okay, you will typically use what's called both a fixed bearing and an expansion bearing. Has anybody in civil land maybe heard those terms before? I'm just curious. Okay, that's okay. All right, so a lot of times in bridges, so you'll use what's called a fixed bearing and an expansion bearing, and really the difference is how the beams or the flexural elements are attached to the foundation, okay? A fixed bearing is basically just going to have a plate with like a circular hole in it, bolt it through, and it's not going anywhere. But an expansion bearing is going to have a slotted hole. So it's actually going to be allowed to move a little bit, okay? And some of you might be thinking, who would want a bridge to move? That sounds crazy, right? Who would want a bridge to move? Well, a couple things to keep in mind. We're not talking about the bridge moving 100 feet, okay? We're only talking about it translating just a little bit. But there's a very specific reason why we would want to allow translation, okay? What's the weather like today? What's the temperature going to be? Like what, 80 degrees, something like that? What's the temperature going to be like 6 months from now or 4 months from now, let's say in February? 30, 20, maybe less, right? So that is a heck of a temperature shift, okay? What happens when we have temperature variation? We have objects that will expand or contract, right? So if we affix both sides and the temperature increases, that beam will want to expand and push the foundation and put a lot of force on that retaining wall. So we actually want to let the beam breathe a little bit so that it can withstand thermal expansion and contraction. Does that make sense? And I'm talking about this from a bridge standpoint, but you're going to find the same idea, for example, in mechanical system design. If you have an element that can expand and contract and it heats up too much, it might cause additional stresses on adjacent elements in the system. Same thing for you biomedical folks as well. So the idea is to keep the system in static equilibrium, but the more restraints that you provide in the system, the more forces you might have to deal with, okay? So the idea, again, the point is to make sure that you're mapping the reality of the system to what support conditions or what boundary conditions that you use. And so in this class, I'm showing you the most common ones for any discipline. Oop. Does that make sense? Okay. So a roller support will allow translation in one direction, and it will allow rotation. It will just prevent translation in that one direction. A fixed support is sort of like that column between the buildings, like being embedded. That's the one where it's my fist. It will withstand translation and rotation. So it, sorry, So a fixed support would have 3 unknowns. And just so everybody's clear, today we are doing simple support problems. We're not even going to touch fixed supports until Monday, okay? So today is a simple support. And by simply supported, if I use the term simply supported, I'm meaning hinge roller or pin roller. Simple supports don't have moments. Fixed supports do. So if you want to know a terminology definition there, that's what I mean, okay? Everybody with me so far? Okay. All right. So these are going to be our most common ones that we utilize, and our goal for the next couple lectures is how to compute these unknown forces, okay? And we're going to, so again, by the very nature of this problem, we have 3 equations, 3 unknowns. That doesn't mean we can't get strategic about how we solve our problems. And I think the best way of going down this rabbit hole is to just do an example. Okay, so I have here a problem. Let's take a look at it. Okay, so, all right. So, this is going to be our first rigid body equilibrium problem. So I have a beam, okay, and it is subjected to a series of loads. So again, imagine the table, but it's not just me sitting on the table, and it's me and a couple of you sitting on the table. What's the force here, and what's the force here, and whatnot to keep the system in equilibrium, okay? A couple things to point out, okay? Because of the nature of this problem, and because I'm going to be dealing with primarily the coefficient parts of these equations, we're not going to see any IJK in this example. This is just going to be force times distance, just straight looking at the problem, okay? All right. Now, I've got 2 support conditions here. I have a support condition at A and a support condition at B, okay? This support condition is a pin support. So remind me, let's see if we're all paying attention. If I have a pinned support condition, how many unknown reactions can exist at a pin support? Not a roller, a pin. 2, right? The triangle support can have a force in the x direction and a force in the y direction, right? The roller at B can only have an unknown force, right? Everybody with me on that? Okay. All right. So I'm going to let everybody draw this out, and then I want to get everybody's attention here, because we've got some important stuff to discuss here, because I want to make sure that we're all comfortable with what we're doing here. I'll give everybody a sec. This is important stuff. Everybody good? Okay. All right. So one of the things that you have to do when you're doing these types of problems is identify your unknowns, but you also kind of have to make some assumptions. Okay, so let me kind of explain what I mean. I have a bunch of forces acting downward. So to keep the system in equilibrium, which direction do you think my unknown vertical reactions are going to act? Upwards, right? Like if I'm standing on top of this table, the table's got to hold me up, right? Okay? So what I'm going to do is here at this triangle, I'm going to draw an upward force, and I'm going to draw an upward force right here. And I'm going to name those. We're going to call that BY. We're going to call that AY. Okay? Now, I want to make a very specific point right now. Okay? If I'm being hyper-specific, I made a guess that these forces are acting upwards. Now, spoiler alert, that guess is correct. Okay? But let us assume that I guessed wrong. Okay? Let's say my guess is incorrect. It does not mean you have to develop significant emotional distress. What's going to happen is we're going to go through the calculations, and if you guess incorrectly, your answer will be negative. So, oh, I just guessed the wrong way. And does that comport with what we've been talking about so far? Well, yeah, think about it. If I have a force that's acting this way, and I tell you that force has a magnitude of negative 20 pounds, that just means it's acting this way, right? It just means it's acting in the opposite direction. So we're guessing that the force acts this way. If we get a negative, just flip it, okay? Now, we do have an unknown right here in the x direction. So we're going to call that AX, all right? But we might talk about that a little bit later. Okay. So far, so good? Okay. Now, so how many unknowns do I have in this system? 3, right? I also have 3 equations of equilibrium. The sum of the forces in the x direction equals 0, the sum of the forces in the y direction equals 0, and the sum of the moments equals 0. Notice how I didn't put a subscript. I didn't say m sub z. And I'm doing that actually for a specific reason here. When we sum moments, notice how what we've had to do, and we've started to broach into this a little bit in our most recent problems, like with equivalent systems, but when we sum moments, we sort of select a point. We say we're going to take moments about that point, right? We're going to take moments about that point, and that's the point of reference, right? Here's the thing. This beam doesn't care what our point of reference is. The answer is the answer, right? So really, the sum of moments can be taken about any point, okay? I can take the sum of the moments about here, 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 here. It doesn't matter, and the reactions will be the same. The reactions will work out. Now, that doesn't mean that we can't be strategic, that we can't choose a point that's going to make our life easier, okay? But the beam doesn't care where we sum moments, okay? That's very important. So far, so good? Now, let's handle this one equation at a time, okay? So I'm going to start off with the simplest one, which is the sum of the forces in the x direction, okay? Now, let me show you what I'm going to do here, okay? I'm going to say, summing the forces in the x direction, I must get 0, but watch what I'm going to do. I'm going to do that. Okay? What I'm doing is I'm writing a little right arrow, and I'm saying that that's positive. So what I'm saying is when I write this equation, I am writing it such that if I have a positive value, it indicates a force to the right. And if I have a negative value, it's a force to the left. I, as the analyst, can do that however I want, okay? I'm going to do it this way, okay? So summing forces in the x direction, the sum of those forces must be 0. I'm going to take right forces to the positive. So again, this is going to be a really easy one. Is this a force acting in the x direction, AY? What about this? What about this? What about this? What about that? The only force that's acting in the x direction is AX, right? Is it positive? Because that's the way we've drawn it, right? So AX is the only force in the x direction, right? And what must it equal? 0. So that, I'm going to call that equation 1, although that's the answer for that reaction. AX equals 0, right? There is no reaction at A. Like, you could technically say there is an unknown and the value is 0. Okay. Now, let's do the sum of the forces in the y direction. I'm going to scooch this up a little bit. Let's sum the forces in the y direction and set them equal to 0. Now, similarly, what I'm going to do is I'm going to choose a sign convention. I'm going to choose upward forces to be positive, right? And what I'm going to do is I'm going to work from left to right, okay? So, do I consider AX? Do I consider AY? Is it positive? Yes. So, AY. What about the 20 kips? Negative. Same thing with the 30 and the 18. So, and then plus by, and that sum must be equal to 0. So therefore, so 20 and 30, 18, 68 kips. Okay, so this is interesting. Equation 1, bless you, equation 1 gave me an answer, right? It said that AX equals 0. I have an unknown and a value. That's not what happened with equation 2, right? What happened with equation 2 is I just have a comparison. Like whatever AY is and whatever BY is, they will sum up to give me 68. But it won't tell me what it is, right? So instead, in order to isolate one of those, I would need to sum moments, okay? Now let's talk about the summation of moments, okay? So if you have a system, right, and you have a bunch of forces all over the place, okay, what you do is you pick a point, okay, and you say, okay, I'm going to take moments about this point. And so for this force, it's that force times the r vector, that force times the r vector, or more specifically, maybe the magnitude of the force times the moment arm, right? So instead of our moments being defined as r cross f, I think we're going to be able to use this definition a lot more easily. Okay? Now remind me, how do we get the moment arm? It's the shortest distance from the line of action to the point in question, right? With me so far? So, let's be strategic about this. I can pick any point I want. I want to select a point that's going to make the math easier. So maybe what I ought to do is select a point through which a lot of unknowns interact, right? So what point do you think would be a natural location about which to sum moments? A. Because if I sum moments about point A, I don't have to consider AX or AY, right? Because AX and AY go through point A and they generate no moment. The same thing would be true if I sum moments about B, right? Because if I sum moments about B, AX and BY go through it. And so I would just be isolating AY. But let's work left to right. I think it's a little easier. So I'm going to sum moments at A. Okay. Now before we do this, this equation is not summing forces. This equation is summing moments. Okay? So what we need to do is select a sign convention for the moment. A moment is a tendency to rotate. Okay? So what I'm going to do is if this is positive x, positive y, positive rotation, I'm going to say that moments going this way are positive. Okay. So let's see if we can work this through. So the idea is that I'm going to keep my eye throughout this equation. I'm going to keep my eye fixed right there. How'd I do? Good. So when we sum moments, we're going to look there. That's where our eye's going to be. Probably borders on creepy. Oh, I'm sorry. Okay. So, if I'm considering point A as the point about which I'm summing moments, does AX or AY generate any moment at A? Okay. Does the 20 kips generate moment about point A? Yes. Let's talk about that 20 kips. If my finger is right here at point A, and here's the 20 kips, which direction is it going to rotate? Is it going to rotate in a positive direction or a negative direction? Negative direction. Okay, so it's going to be negative 20 kips times what? Remember, so watch this. So here's the point. Here's the line of action. Here's the force. That's the force. The moment arm is the shortest distance from the point in question to the line of action of that force. So what is the shortest distance from A to the line of action of the 20 kips? 6 feet. Okay, let's keep going. Does the 30 kip generate moment? Which sign, positive or negative? Negative, okay. What is the moment arm going to be for the 30 kip load? Say it again. 15 feet. It is not 9, okay? Because our eye is fixed at A. How far is the line of action of that 30 kips from A? It's 15 feet. Does that make sense? So, tell me what to write for the 18. What am I going to do?
Negative 2k times
22 feet. So what do I do for the BY? Does the BY generate moment? And so what do I do? Plus BY times 30 feet. Okay. All right. So, how many unknowns are in this expression? 1. So I can solve for BY directly. All right. So 20 times 6 is 120. So minus 120 foot kips. Minus 30 times 15, that's 450. Minus 18 times 22. I don't know if I'm that good. 396. Plus BY times 32 feet equals 0. So I can...
Shouldn't BY be times
30. Why did I say 32? It's 30. You're right. I'm looking ahead is what's happening. You'll see why. All right. So I'm going to add the 120, the 450, the 396 over to the other side. So BY times 30 feet is 120 and 450 and 396 is 966, right? I divide both sides by 30, and therefore BY is what?
32.2.
You can see I was looking ahead, yeah. So, but more specifically, it's not just 32.2, it's positive 32.2 kips. You're right, but you're right, yeah. So it's positive 32.2 kips. So I really made it a point to draw this positive. Why? Why did I say it's positive? Remember, I guessed that this was going up. I just guessed. And I got a positive value. See, here's the thing. This positive or negative doesn't matter. How do we define a vector? This is a vector. How do we define a vector? A magnitude and a direction. The magnitude, we all agree with, 32.2 kips. But the direction is dependent on what you guessed. So this positive or negative doesn't matter. What really matters is that it's 32.2 kips. Now, from a math perspective, we'll go ahead and say that this is equation 3. But when we write our answer, I don't care about positives and negatives. I want magnitudes and directions. So far, so good? So, tell me what to do. Now, what do I do? Solve for
A1.
Exactly. By plug and chug, right? So, And so if I plug in 32.2 and I solve for AY is going to be 35.8. And that it is also positive, right? So I think the point I want to make is this. What is the answer to this problem? The answer to this problem is AX equals 0, AY is 35.8 kips upwards, and BY is 32.2 kips upwards. Okay? And that's the answer. Those are the forces necessary to keep the system in equilibrium. Does that make sense? That should be hopefully a pretty straightforward problem. Okay. Yes?
So if we had guessed that they went up and our answers came out negative, we just flipped them.
Write them downwards. Yes. You're exactly right. And I'm gonna maybe try and walk you through what happens with that on the next example. Okay? You'll see what I mean. Okay. Does everybody have this? Okay, can I move on to the next one real quick? And we'll see if I finish it. I probably won't, but we can pick this up on Monday. Because this next one won't impact your homework. So. Okay. So here's this one. Okay. I have a crane that's picking up a pretty heavy load, a 2,400 kilogram box. That's heavy, so I hope they're using proper OSHA safety procedures. The crane itself is not as light as a feather. The crane itself has a mass of 1,000 kilograms. Did I say weight of 2,400 kilograms? I hope I didn't say that. Mass of 2,400 kilograms. So it's held in place by a pin at A and a roller at B. Okay? Now, one of the things that this is a term that I'm throwing out, is a center of gravity. We're going to talk about that later. Okay? But for the purposes of this example, what we can say is that the crane has a mass of 1,000 kilograms, and we'll assume that that mass is lumped right here at the center of gravity. Okay? So the goal is to compute support reactions. Okay? Now, I'm giving you 1,000 kilograms and 2,400 kilograms for the box. We're going to need to say, okay, what are we going to do here? This is going to be weight equals mass times gravity, right? So we're going to have to convert that. So this one's going to be, just 9810 newtons or 9.81 kilonewtons. We'll squanch that a bit. And this one's going to be 23,544 newtons or 23.544 kilonewtons. Okay. Does everybody have this? So I don't think we're going to finish this problem today because I want to give this problem its due time. Maybe we'll just come right in on Monday and do it. But here's what we're going to do for our free body diagram. Okay. So I'm going to do my best to sort of draw out this crane. Let's lower this a little bit. Okay. And we're going to say that there is a load here of 23.544 kilonewtons. And we also have a load right here of 9.81 kilonewtons. Okay? Let's put our dimensions on here. So from the problem, this is 4 meters. This is 4 meters and 2 meters. Now, let's look at these support conditions, okay? So this one right here is going to be our pin support, and this one's going to be our roller, because you can see that, you know, there's sort of that rocker wheel thing going on. So I'm going to draw it like this. And I'm going to draw this like that. Okay? Now, here's what I'm going to do, and we're going to address this problem on Monday. I'm going to do this. I'm going to assume, so how many reactions are at, so this is point A, this is point B. How many reactions are at point B? 1. And it's got to go in the direction of the roller. So I'm going to do that, call that BX. And for the support at A, how many reactions do we have? 2. And so what I'm going to do is sort of do that and that. And so we'll call this AY, call this AX. And don't forget that this dimension here is 1.5 meters. Now I'm going to put a pin on this problem today, and we'll pick this up on Monday. But what I will tell you is that one of those guesses is wrong. One of them's wrong, okay? In terms of the assumed direction, okay? And I want you to have, I don't think this is going to affect your homework assignment, so we can pick it up on Monday, but I want you to have experience with what if you make a wrong guess, what happens? It's not the end of the world, so. Sound good? All right, I'm going to go ahead and call it there. I'll pull up the code one more time, and then I will see you all on Monday. On Wednesday, on Monday.